Hello everyone and welcome to the channel. In this video we are going to do a quick revision for heat and mass transfer or HMT. There are two units in heat and mass transfer. Unit 1, fundamentals of heat transfer. So 2 units for the Insem examination. A total there are 6 units as it is. So unit 2 is heat transfer through extended surfaces and transient heat conduction. The first unit has 24 theory plus derivations. I'm not including numericals right now. This is only theory plus derivations and important theory and derivation, and this is 20 important theory and derivations. All of this we will be seeing in this video, so keep watching. We'll go on to our first question. So our first question is differentiate between steady state and unsteady state of heat transfer. First we will see what is steady state and what is unsteady state. So we can easily write the differentiation in the table. So in steady state, the temperature remains constant and it does not change with time. Temperature is constant, that is, it does not change with time. Next is internal energy remains constant under the steady state. Internal energy remains constant. And it also means that the rate of heat energy into the system is equal to the rate of heat energy out of the system. Rate of heat energy in the system equals rate of heat energy out of the system. And under the unsteady state, we have the temperature varies with time. Temperature is not constant. Temperature varies with time. Moreover, it is function of both location and time. So space and time, both the factors are considered. Function of location and time. And next is the example. So we will see example for each. So for steady state, the example is heat exchanger, flow of electricity, flow of current in conductors, flow of current in conductors. And the next is flow of fluid in pipes, that is the steady state. For unsteady state, the example is cooling of automobile engine. It is unsteady. It is an unsteady state. Cooling of automobile engines. Next, freezing of food in the refrigerator. Freezing of food in the refrigerator. And next is heat treatment of metals by quenching. Heat treatment of metals by quenching. So this is it. These were the points. We'll see it once again. Steady state, temperature does not change with time. Internal energy remains constant. Rate of heat energy in the system equals rate of heat energy out of the system. In unsteady state, temperature varies with time. it is a function of location and time. And next, the examples. For steady state, the examples are heat exchanger, flow of current in conductors, flow of fluid in pipes. And for unsteady state, it is cooling of automobile engine, cooling of automobile engines, and refrigeration of freezing of food in refrigerator, and heat treatment of metals by quenching. This question came in Sppu in May 2014. Sppu May 2014. The marks are not mentioned, but there are chances this might come again. So we will see our next question. Explain Fourier's law of heat conduction. This is how the relation looks like. This is how it is mathematically expressed. We will try to write it in words with the help of this mathematical expression. So it says it is the rate of heat flow, which is this, the rate of heat flow in a solid, simple homogeneous solid body, in a simple homogeneous solid is directly proportional So this is the proportionality sign. Area measured normal to the direction of heat flow. Area measured normal to the direction of heat flow, and the temperature gradient in the direction of heat flow, and the temperature gradient in the direction of heat flow. So this is our rate of heat transfer, this is our area normal to the direction of heat flow, and this is our temperature gradient in the direction of heat flow. So this is normal, and this is in the direction of heat flow. Okay, so we will just define below what those things are. So Q is the heat transfer rate, its unit is joules per second or watt in the given direction. A is the area normal to the direction of heat flow, it is the unit is m square. Dt is temperature difference between two faces of block of thickness dx. There is a block of thickness dx, and the difference between the temperature difference between its two faces is dt. Dx is the thickness of a solid body, and dt by dx is the temperature gradient we talked about here in the direction of heat flow. And now the proper formula, so we remove this sign, proportionality sign, and put it equals to and minus k over there, and k is called coefficient of thermal conductivity. K is called coefficient of thermal conductivity. And why is there this negative sign is there? It is because dt is negative in the direction of heat flow, that is positive x direction, because the heat always flows from higher temperature to lower temperature. So heat always flows from higher temperature to lower temperature, but here we are not considering that. That is why we need a negative sign over here. And this basically also implies that k has a positive sign, and the unit of k is watt meter degree Celsius. Okay, this was the question. It came in exam in August 15 for the Insem examination, so there are chances this might come this time as well. Our next question is define thermal conductivity. it came in exam in August 17 and October 19 in semester exam. So basically it is the ability of material to conduct heat through it. But we have already seen the formula, that is Q is equal to minus Ka dt by dx. So we will try to rearrange this formula and try to make it for thermal conductivity. So how can we do it? Just forget this part, we will make it on our own. For K, we will just keep K to this side and take A over there, dt by dx will rearrange. Then the amount of heat flow rate per unit area, so it is upon, so per unit area normal to the direction of heat flow, so that was there before only, normal to the direction of heat flow through unit thickness of material per unit temperature difference, through unit thickness of material per unit temperature difference. And this is our definition, this is our statement: the amount of heat flow rate per unit area normal to the direction of heat flow through unit thickness of material per unit temperature difference. Okay, so our next question is define apparent thermal conductivity. In this, heat transfer of convection and radiation is negligible, and apparent thermal conductivity is the ratio of thickness of interface material to the thermal impedance, and it is also called effective thermal conductivity, and it is less than the true value of thermal conductivity. So this is it about it. One thing, negligible convective conduction and radiation heat transfer, ratio of thickness of interface material to the thermal impedance, also called effective thermal conductivity, and less than true values of thermal conductivity. I'll repeat once again: negligible heat transfer from convection and radiation, ratio of thickness of interface material to the thermal impedance, effective thermal conductivity, it is also called effective thermal conductivity, and its value is less than the true values of thermal conductivity. So this question, general heat conduction equation in Cartesian coordinates, came in exam for like 4 to 5 times already. So I think that this is very important. We have to start this by drawing a cube. So this is the cube oil, and give it directions x. So this is x direction, this is z direction, and this is the y direction. So here dqx plus dx, this is del x, this is del x, this length is del x, this length is del z, and this length is del y. What we have to do here is we have to find the general heat conduction equation for the in Cartesian coordinates. So first we will just write whatever that, consider a small rectangular volume of size del x, del y and del z parallel to the three axes in the medium. Let T denote the temperature at the center. Let T denote the temperature, and then also let the material be anisotropic, implying that the thermal conductivities have the values kx, ky and kz in x, y and z direction respectively, so they are not same. Later on we are going to derive that what if they are same, but right now they are not same. So now we will first see the energy balance equation, how it is. So in energy balance equation, heat conducted, net heat conducted plus net heat generated, net heat conducted plus heat generated equals energy stored. Okay, now what we have to do is we have to apply the Fourier's law of heat conduction. What is Fourier's law of heat conduction? We have previously seen it as Q equals minus Ka dt by dx. This is Fourier's law of heat conduction. So now the heat entering will be dq, as we have written over here, dqx. It will be equal to minus kx a dou t by dou x, and a over here will be the area, which is del y and del z. Okay, so this will become kx del x or del y del z dou t by dou x. Then the heat leaving will be dqx plus dx. This is the heat leaving. We apply Taylor series over here, and then it becomes, I'm not explaining right now, first we have to write this thing, plus dou by dou x dqx, the same thing, and then del x. This is the value. For the net heat flow in the element, we just subtract it. So this minus this minus this, so qx minus dqx plus dx. So it becomes minus dou by dou x dqx del x. How? So this is the first value, and you are subtracting this from it, and that is why we have this thing. So this minus this, so this became 0, and then minus sign over here, so this directly came over here. So this is for x direction. For y and z direction we will have the same thing, but before that we have the formula for dqx, that is this very formula. So we will just substitute it over here in this, and this becomes dou x. This is also negative, this is also negative, so eventually this is also negative, this is also negative, so it will become positive. Kx dou t by dou x del x del y del z. This is our equation for net heat flow into the element in x direction. For y direction only, this will be y, this will be y, this will be y, this will remain same. So we just have to derive for x. We'll see from the starting what we did. So we did this minus this. We wrote Fourier's law and wrote this. We started substituting. A, we decided that it is dou y by dou z for x direction. For y it will be dou z dou x, and for z it will be dou x and dou y. Okay, so we will just go ahead and write down the formulas for net heat flow in x we have done, y and z direction. Actually this derivation is a bit huge, so even I'm getting tired while explaining it. Dou y ky dou t, dou y, del x, del y, del z, dqz minus dqz plus del z equals dou y dou z kz del t del z dou x dou y dou z. Okay, so now when we add this, we will get the net heat flow into element by from all the directions. So we have to add whatever we have received. So it will essentially become dou by dou x bracket kx t by dou x plus dou by dou y ky dou t by dou y plus dou by dou z kz dou t by dou z, and in multiplication this del y and del z. Okay, so this is our equation for net heat flow from all the directions. Previously we did in x, y, and now it's in all the directions. We go ahead and then we say that the G, we are naming G as heat generated per unit volume. Heat generated per unit volume per unit time. We are going to need this later on, and we write volume. So this is volume of a cube, so it will be dou y dou z dou x dou y dou z. So volume of the cube, and the internal heat generation will be this multiplied by this. Internal heat generation will be this multiplied by this. So G into dou x dou y dou z. Okay, and now heat gained by the element will result in energy storage, and we know the net heat storage. The net heat storage is given by mCp delta T, which is now m is equal to rho v Cp and del T over here for us. So we know what it is. V is this, so it becomes rho Cp del T del x del y and del z. Now whatever equation we wrote before this, we have to substitute everything we have derived till now in this equation. So what will it become? The energy net heat conducted is this. Okay, the internal heat generation, that is heat generated within the element, is this, and it equals to this. This is Cp del T. So it is equal to this. So the final equation we receive is dou by dou x kx dou t by dou x plus dou by dou y ky d by dou y plus dou by dou z kz z del x del y del z del t plus this thing del x del y del z g equals rho Cp del T x y z, right? But now we can see that this yeah, it's here as well, this, and so it is in the given time, so it should be also multiplied by del T. My bad, I forgot to write it over here. It is in the given time, that is why we have to write del T as well over there. So this, and we just multiply it by we just divide it by this entire thing, and it simplifies. It becomes dou by dou x kx dou t by dou x plus dou by dou y ky dt by s z kz z plus g equals rho cp t by t. So this is our final equation for this. Now when you say for isotropic element, kx equals ky equals kz equals k. So here all the k will be equal. You can take them out of the bracket and you can multiply, you can divide the entire thing by k. That is how it works. But that is for that is very easy, so you guys can get it. We'll go on to the next question. Now we are going to see something called thermal diffusivity. What is for thermal diffusivity? It is defined for isotropic condition. Now what is isotropic condition? As I explained earlier, isotropic condition means kx equals ky equals kz equals k. So k is equal in all the directions. Then the equation becomes something like this, k common, and when we divide by k, it becomes g by k, and this becomes rho cp by k. Now rho cp by k is defined as 1 by alpha, where alpha is defined as thermal diffusivity and its unit is meter square per second. Higher the thermal diffusivity, higher the heat diffusion in the material. This is how it is defined. This question also came in the exam. Define thermal diffusivity for, I guess, in the Insem examination itself. So yeah, we will go ahead and see Poisson's equation, Laplace equation, and there was one more equation. So Poisson's equation is, it is in steady state. So if it is in steady state, the temperature won't change with respect to time. So del T by del T, so temperature and time is 0. So this entire thing becomes 0 over here. Now our equation will become, so this thing becomes 0, so this will also become 0. Our equation is x square y square del z square plus g by k equals 0. This is our Poisson's equation. Maybe even Poisson's equation can directly be asked in the exam, and it is very easy. So we'll go ahead and see the Fourier's equation. So the Fourier's equation says that there's absence of heat generation or release of energy in the system. Okay, so G is equal to 0. Now if G is equal to 0, from this equation this will be 0. Our equation will become square by x square plus t by del y square plus dou square t by dou z square equals 1 by alpha t by dou t. This is our Fourier's equation. Now in Laplace equation, so remember in previously in Poisson's equation this was 0, in Fourier's equation G was 0, now in Laplace equation both are 0. So G is also 0 and del T by del T is also 0. We will have del x square plus del square t del y square plus del square t by del z square equals 0. And this is our Laplace equation. This can also be written as this. This is the Laplace equation. Okay. I think I'll have to cut short the video. We won't be able to do all the 44 questions, and maybe we'll do a few numericals because it's already 8:15 and I want this video to be uploaded by like 11 p.m. or 12 a.m. So I think we'll cut it short so at least the video could be uploaded. This next question is write a note on heat flux boundary condition. So heat flux is given by Q by A. Now if you remember what this Q by A is, it is Fourier's law of heat conduction, dt by dx. So two boundary conditions can be defined, x naught and q naught and ql. So at left face, see this is the left face, this left face x equals 0. So heat flux entering the wall is q naught equals minus k dt by dx at x is equal to 0. Then at the right face, x is equal to L, and heat flux leaving the wall will be QL minus K dt by dx, x equals L. Now suppose one face, that is this x is equal to 0, is insulated, so Q naught will be 0. So if Q naught equals 0, then K is not 0. We know that K cannot be 0. So dt by dx at x equals 0 is 0. This was the entire answer for heat flux boundary condition. So next question we are going to see is heat conduction through cylinder with heat generation. This question came in semester exam for August 2017. So we will see. First we will write it down that what Poisson's equation is for a cylinder, that is 1 by r d by dr, 1 by r d by dr r dt by dr plus g by k equals 0. So this is for steady state one-dimensional heat conduction with internal heat generation. So assuming constant heat generation and constant thermal conductivity, the above equation we can write it as d by dr r dt by dr equals minus g by r or g by k into r. So this r went over here and we multiplied it simply. We just considered that constant heat generation is there and constant thermal conductivity is there. We will integrate this r dt by dr equals minus g by k r square by 2 plus c1. So c1 over here, because we integrated, we will just rearrange it quickly. Dt to one side by dr equals minus g by 2k r plus c1 by r. This is the equation after first integration. Then the next we will integrate it once again. This will be t minus g by 2k r square by 2 plus c1 log of r plus c2. This is after doing the second time integration. Now we will see what we have to do ahead. We have some boundary conditions. When r is equal to 0, there will be r will be 0 and the temperature gradient will be 0 as well when r is equal to 0. So r is equal to 0, dt by dr equals 0. When we substitute this in the equation, in this equation, the above, we get c1 equals 0. And when r is equal to r, t is equal to tw. So what is TW? TW is the surface temperature. When R is equal to R, when R is equal to R, T is equal to surface temperature. So when we substitute it in this equation, the second equation, we get TW, which is this, equals minus G by 2K capital R square by 2 plus C1 is 0, C2. When we write the value of C2 from here, it will be TW plus G by 2K R square by 2. Now we have the value of C2. Now we have received the values of C1 and C2. C1 equals 0, C2 equals this. We will substitute that in this equation. So it will become T equals minus G by 2K R square by 2 plus TW plus G by 2K R square by 2. When we rearrange, we get T minus TW equals G by 2K R square by 2 minus small r square by 2, and when we take this 2 out, we get 4K R square minus R square. In this, the problem was given that prove that the maximum temperature at the center of cylinder. So at the center of cylinder, this R will be 0. So the equation will look like T minus TW G by 4K R square. When we put this T over there, TW plus G by 4K R square. This is our answer for cylinder. We have similar thing for sphere as well. That is TC, temperature at the center. This is for sphere. Till this it was for cylinder. This is done over here. Now you will see for sphere, TC is G by 6K R square plus TW. So Poisson's equation for sphere can be written as 1 by R square d by dr r square del t by del r plus g by k equals 0. So only in this equation it is multiplied by r everywhere, and that's the equation essentially. So everywhere r is multiplied by r, it became r square. So in this also we have to do the same thing. We have to integrate this equation twice, and after C1 equals 0, find the value of C2, and we get this answer. This was also asked in Insem exam in 2017 August. We will now see a question from types of fins and its application. This question came in exam for 2 times, August 15 Insem on August 18 Insem exam. One is give at least 4 examples of use of extended surfaces, that is fins, for engineering applications, and state the application of extended surfaces. So these are the 5 different types of fins you can see on the screen. The fins are generally used to increase the rate of heat transfer. So the fins are normally made of materials such as copper, aluminium, steel or brass. They are of different types. The fins which are attached to the plane walls are called straight fins. The fins may be also of cross-sectional area, right? Rectangular plate fins, or varying cross-sectional area like tapered fins, as you can see in the diagram, and radial plate fins. The use of plate fins in ice, there's use of plate fins in IC engines, and annular fin is attached circumferentially to a cylinder. The pin fins or spline is an extended surface of circular cross section. The diameter of pin fins is less than its length. The applications are generally usually the pin fins are provided on surfaces where convective heat transfer coefficient is low, as in case of gases. Extended surfaces are used in radiators, cylinders of compressors and engines, transformers, motors, and various types of heat exchangers. I'll repeat. Fins are used in radiators, cylinders of compressors and engines, transformers, motors, and various types of heat exchangers. The geometry of fins are based on the cost, efficiency, performance. These are few questions from unit 2 related to fins, and I found them like they are very important, asked in exam 4 to 5 times each of these, but I cannot explain them in the video because of time constraint. But don't fail to revise these questions. They are available, the entire explanation of these questions is available on eKida channel. It's like 12 to 15 minutes of videos for all of these 5, and it's explained well, so you guys can go and watch it. Thank you so much for watching the video, and sorry because I could not explain the numericals and lot of parts, even theory parts, because of the time constraint. I wanted to be uploaded by 12 or 11. Hopefully it will be, but because of that I couldn't explain a lot of things, and even the syllabus is huge. So sorry for the inconvenience, but thanks for watching and all the best for the exam. Hopefully the next videos would be better and more syllabus would be covered in it.